Integrated problem number 5. So we're going to answer a series of questions built around this idea of urea being a common fertilizer. So urea, which is CH4N2O, is a common fertilizer that can be synthesized by a reaction with ammonium and carbon dioxide. And typically the secondary product of this, even though it's not on here, is water. So we're going to write a balanced chemical equation representing this reaction. We're going to form this urea from the reaction of ammonia, which is NH3, plus carbon dioxide, CO2, to form urea, CH4N2O, plus water. When we do this reaction, right, in order to balance it, first we're going to look at the nitrogen. There's one nitrogen here, two nitrogens there, so we need a 2 in front. All right. We have now 6 hydrogens, 4 here plus 2 there, is 6 hydrogens on this side. Carbon, we have 1 carbon, 1 carbon. Oxygens, 2 oxygens here. 1 plus 1 is 2 oxygens there. So now we have a completely balanced reaction. So then we're going to identify all the species here in the balanced reaction as an element or a compound. So we have NH3, CO2, CH4N2O, and H2O. Right, so first we're going to identify it as an element or a compound. We see all of these are a mixture of more than one element, so all of these would be considered compounds. So then the other question is, for these compounds, is it molecular or ionic? Right. So if we look at this first one, NH4, again from the periodic table, especially this one, we see that hydrogen is considered a non-metal. So we have hydrogen and nitrogen, which is all non-metals. So NH4 is a molecular compound. CO2, again, carbon and oxygen are both non-metals, so this is also a molecular compound. C4N2O, so now we have nitrogen, oxygen, carbon, and hydrogen, all we're going to consider compounds, so this is also a molecular compound. And finally, oxygen and hydrogen, also a molecular compound. So in this case, all of these are compounds, and they're all considered non-metals, so they're all molecular compounds. Okay. So in an industrial synthesis of urea, a chemist combines 136.4 kilograms of ammonia with 211.4 kilograms of carbon dioxide. How much urea is formed? Right. Looking at this problem, we're given information about both of these reactant compounds. So what we have here is a limiting reagent problem. The amount of product, or urea, that is going to be formed is going to be determined by which one runs out first. So the simplest way to answer this is actually what happens if we convert all of this 136.4 kilograms of ammonia to urea, and what happens if we convert all of the 211 kilograms of carbon dioxide to urea. The one that produces the smaller amount is going to actually be the amount that's formed. The one that gave us that is going to be our limiting reagent. So we're going to do this problem where we take the 136.4 kilograms of NH3 and convert to urea. So the first thing we have to do is go to grams. So we're going to take this, there's 1 kilogram is 1 times 10 to the third grams. Now this balanced chemical equation is in terms of moles, so we have to convert this amount to moles. So the molar mass for this from the periodic table we see is 17.034 grams of NH3 for every 1 mole of NH3. From the balanced chemical equation, for every 2 moles of NH3 that react, we get 1 mole of urea, CH4N2O. And it's asking about how much. Typically that's in a mass, so we can convert to grams there using the molar mass of urea, CH4N2O. So we're going to take the mass of the carbon, hydrogen, nitrogen, and oxygen, add them all together, and we get 60.062 grams of urea. Right. Cancel the units, and we're left with a mass of urea. We do that. Since we have kilograms here, I'm also going to convert to kilograms here, although it's not necessary. So we have 1,000 grams and 1 kilogram. So when we do this, we get 240.5 kilograms of urea. If we convert all of this ammonia to urea. Okay, we're going to repeat that same sort of process with the carbon dioxide. Again, convert to grams. For every 1 mole of carbon dioxide, we get 44.01 grams. Again, that comes from the molar mass, which we get off the periodic table. Well, the sum of the periodic table. From the balanced chemical reaction, now for every 1 mole of carbon dioxide that reacts, we get 1 mole of urea. And again, we're going to go back to a mass here, so we have 60.062 grams of urea for every 1 mole of urea. And just for consistency's sake, I'm going to convert back to kilograms, just like I did above. And here we end up, again, looking at our units. We're left with kilograms of urea, and we end up having 288.5 kilograms. Right? So the one that's going to give us the smaller amount, we're only able to produce the smallest amount. So we see that we're going to produce 240.5 kilograms of urea. Because once this stops, that amount is done, all of the ammonia is consumed, and we'll have some leftover carbon dioxide. So this, the limiting reagent, is the NH3. Right? All right. So when we did that, if we actually get 168.4 kilograms of urea, what is our percent yield? Remember that percent yield is equal to the actual divided by the theoretical times 100 to make it a percent. So in this case, we're going to take the actual, which is the 168.4 kilograms, divided by the theoretical. We said we should have been able to produce 240.5 kilograms, times 100. We get a percentage of 70.02%. Right? So the limiting reagent, the one that runs out first, or gives us the smallest amount, gives us the theoretical yield. We actually run that experiment, we get the actual yield. The actual divided by theoretical times 100 gives us a percent yield. So, if this reaction was carried out as a solution with a volume of 10 kiloliters, what is the actual concentration of urea in this final solution? Right. One of the keys here is in the final solution. We actually made 168.4 kilograms of urea, right, from this previous problem. Right, so we want to know the concentration. When we talk about concentration, we typically talk about that in terms of molarity, or moles per liter. Right? So when we talk about a concentration, we can abbreviate it as this brackets, which we talk typically about it in molarity, which is moles of solute per liter of solution. So if we have 168.4 kilograms of urea, we have to convert that to moles and then divide by the volume in liters. So we're going to work backwards from what we've done before. 1 kilogram is 1 times 10 to the third grams. And for urea, we have 60.062 grams of urea per every 1 mole of urea. Right, so now we're left with moles of urea. We want molarity, which is moles per liter, so we have to divide then by this volume in liters. 10 kiloliters. We don't want kiloliters, we want liters, so just like all the kilos, there's 1 times 10 to the third liters in 1 kiloliter. Again, now we're going to end up with units of moles per liter, which is this molarity. Multiply the things on the top, divide the things on the bottom, we get a molarity of, again, we're going to assume this has 2 significant digits, so I'm going to report the answer as 2 significant digits of 0.28 molar urea, or CH4N2O. So what is the concentration of the excess reagent in this solution? Well, there's 2 ways to do that, to answer this question. We want to know the information about the amount of excess reagent we had. All right, so we want to know how much of this is, of the 211.4 kilograms, is left over at the end. What I'm going to suggest we do is we look at how much wasn't formed. How much urea wasn't formed from the carbon dioxide. So we're going to take the mass that was formed and subtract it from the mass of what we could have formed given the amount of carbon dioxide. Right? So we know we formed, we could have formed from this limiting reagent problem 288.5 kilograms of urea could have been formed from the carbon dioxide. We actually only formed in our reaction 168.4 kilograms of urea. So that means that we have 120.1 kilograms of urea not formed because of the amount of carbon dioxide that wasn't able to react. Right? So then we can then take this amount of urea not formed and convert it back to the carbon dioxide and make sure it's in terms of concentration. So we're going to take this 120.1 kilograms of urea, convert to grams, convert to moles, 60.062 grams. Right? But we're not interested in the amount of urea, we're interested in the amount of the excess, which is carbon dioxide. So this excess reagent is carbon dioxide. So again, from our balanced chemical equation, for every 1 urea we reacted 1 carbon dioxide. So 1 mole of CH2H4N2O, we get 1 mole of CO2. Right? So now we're in a quantity in terms of carbon dioxide. At this point we can either go to grams, amount of excess, but we want a concentration. So we want moles per liter. So we're at moles. We're going to then divide by our volume. Again, we're going to convert it to liters to make it moles per liter. When we do this, again, based on this being two significant digits, we will find that we have 0.20 molar CO2 in excess. Right? So we have a concentration of 0.20 molar left of our carbon dioxide. Right? The other way we can do this is we could take and figure out, since we know we formed 168.4 kilograms, we could figure out how much carbon dioxide was actually used and do the subtraction there. In this case, because we weren't going back to grams, we wanted a molarity. This method is a little bit more straightforward. But either approach is fine. Okay. So, remember that we had a percent yield in this first one of 70.02%, which isn't great. So we have our chemist here is going to try to improve the efficiency or improve on that percent yield by modifying some of the conditions. He performed the reaction on a smaller scale to test this hypothesis, this changes he made, and this time using a concentration of ammonia of 0.12 molar and a concentration of carbon dioxide of 0.11 molar, all in a volume of 2.5 liters. What would be the theoretical yield in grams for this reaction? Again, because we now still have an amount of both reactants, this is a limiting reagent problem. But now instead of talking about grams, we're talking about our amount in concentration. So we're going to start then with this amount of ammonia and figure out if we convert all of this ammonia to urea, how much mass would we get. Right. So for information for urea or ammonia, we have 0.12 moles of NH3 per liter of our solution, per 1 liter. Right. We have 2.5 liters of solution, so in that we're going to have a certain number of moles. Right. We don't care about the carbon dioxide, we care about the urea, or the ammonia, and from our balanced chemical reaction, for every 2 ammonias that react, we get 1 urea out. So 2 moles of NH3 for every 1 mole of CH4N2O. Right. Now we want a mass, so we're going to use our molar mass of urea, which was 60.062 grams. And since we want a mass in grams, this is where we're going to stop. Again, we do the math for this problem, and we're going to see that we get a mass of 9.0 grams. Again, repeat this process instead of using the ammonia, using the carbon dioxide, 0.11 moles of CO2 for every 1 liter. We still have 2.5 liters. They're reacting in the same container. So again, back from our balanced reaction, now we have a 1-to-1 molar ratio. So for every 1 mole of CO2, we get 1 mole of CH4N2O. And to get a mass, we multiply by the molar mass, just like we've been doing all day. And in this case, we see that we get a mass of 16 grams of urea. So just like before, we're going to choose the smaller amount. So our theoretical yield in grams is 9.0 grams of urea. So if we did this test and the chemist actually got 0.18 molar. Was this successful? So what we want to know is, did the percent yield increase? Right? So we're going to convert this 9 grams of urea back into a concentration in this reaction vessel. Right? So we're going to take the 9.0 grams of urea, convert it to moles. So that gives us moles of urea. We want now a concentration in moles per liter. So we're going to have to divide by the volume in liters, which was 2.5. So when we do this, we get 0.060 molar. Right. So we can calculate a percent yield in this new reaction as being the actual amount, 0.060 molar, oh, sorry, this should actually be 0.060 molar. Oh, 5.8. That's the theoretical yield. Divide that into the actual yield times 100, and we get 96.7%. So when we do that, we see that we went up from 70.02 to 96%. So yes, this improvement, the method has improved.